All right, let's dive right into this. Welcome to this explainer. Today we're taking a magnifying glass to the internet's most crucial piece of invisible plumbing. We're going to dissect the anatomy of the TCP header. If you've ever wondered how the internet actually functions behind the scenes, how messages get from point A to point B without just collapsing into total chaos, well, this is where the magic happens. I am absolutely thrilled to unpack this with you today. So think about this. How exactly does data guarantee its own delivery? It's kind of a profound problem when you stop and think about it. The internet is this wild, totally unpredictable network. Wires get crossed, signals drop, traffic gets massively congested. And yet, when you load a web page or send a critical message, it arrives intact. How does a raw stream of ones and zeros navigate all that chaos and make sure it arrives perfectly?
Well, the answer lies in the TCP header. Our source defines it as a collection of fields used to control the reliable transmission of data between devices. But honestly, think of it less like boring code and more like the ultimate, ultra-secure, highly tracked shipping label attached to every single piece of data sent over a TCP connection. This header is literally what transforms an unreliable network into a rock-solid guarantee.
Now, a raw TCP header can look like a giant wall of jargon, but don't worry, we're going to logically break this down together. Here is our roadmap. First, the digital delivery problem. Second, addressing the data. Third, maintaining perfect order. Fourth, the command center flags. Fifth, traffic control and integrity. And finally, number 6, delivering the payload. Let's get right into it.
Starting off with Section 1, the digital delivery problem.
You see, before a packet can even think about leaving a device, it needs a basic foundation. Just like the regular postal service, the very first thing our TCP shipping label needs to figure out is identity. It needs to know exactly who is sending the package and exactly who is receiving it. Without this super basic routing information, well, the data has absolutely nowhere to go.
Which brings us to Section 2, addressing the data.
Let's look at the actual fields handling this routing. Networking is for sure a two-way street. So first up, we have the source port. It's 16 bits in size, and it specifies the port number of the sender's application. Basically, it acts as your return address. And on the flip side, we've got the destination port, also 16 bits, which specifies the recipient application's port. Together, these 32 bits are absolutely crucial because they make sure your web browser's request doesn't somehow end up getting delivered to your email app. That would be a mess, right?
Moving right along to Section 3, maintaining perfect order.
Okay, so once we know where the data is actually going, we hit a new snag. When a file gets sent, it gets chopped up into tons of tiny pieces. To keep them from getting hopelessly scrambled in transit, the TCP header uses a really massive number space. We're talking fields that are 32 bits in size. And just to put that into perspective, a 32-bit number gives us over 4 billion, yes, billion with a B, unique possibilities. You literally need a scale that huge to meticulously track the sequence of millions of data bytes zooming between devices.
So how is that huge 32-bit space actually used? Enter the sequence number. This field contains the sequence number of the very first data byte in the current segment. Think of it as the ultimate tracking number. It tells the receiving device exactly where this specific piece of the puzzle fits, which means it can reassemble everything in perfect order, even if the pieces happen to arrive completely out of whack. And this creates this really cool back-and-forth heartbeat between devices. Let's walk through the rhythm here. Step 1, the sender fires off a segment stamped with that sequence number. Step 2, the recipient gets it and sets an ACK flag. We'll get to flags in just a second. Step 3, the recipient sends back an acknowledgment number, which is another massive 32-bit field. But here's the kicker. This number actually represents the exact next sequence number the recipient is expecting to see. It's just a continuous rapid-fire loop of sending, confirming delivery, and asking for the exact next piece.
All right, Section 4, the command center flags.
So while those sequencing numbers are absolutely huge, the header also packs some incredibly tiny rapid-fire control mechanisms. Inside the 8-bit control flags field, we have these individual 1-bit switches, literally just a 1 or 0. But man, they dictate the entire core behavior of the connection. For instance, URG means the urgent pointers field is significant. ACK makes the acknowledgement field valid. PSH triggers the push function. RST, that'll just instantly reset the connection. SYN synchronizes those sequence numbers when you first connect. And FIN smoothly tells the other side, hey, no more data from the sender. Just 6 microscopic switches running the whole show.
Next up is Section 5, traffic control and integrity.
Okay, we've ordered the data, we've set the rules, but how do we pace things out and ensure absolutely nothing got corrupted? Well, the TCP header dedicates 3 specific 16-bit fields just for safety and pacing. First is the window. This indicates the sender's receive window size, kind of acting like a traffic cop managing flow control. Then, the checksum. Think of this as your tamper evidence seal. It detects errors in both the header and the data itself. Finally, we've got the urgent pointer. If that 1-bit URG flag we just talked about is set, this points directly to the sequence number of the last urgent data byte, which basically lets critical data jump straight to the front of the line.
We've also got 2 small, contrasting 4-bit fields just to keep the structure tight. On one side, there's the super practical data offset. This specifies the size of the TCP header in 32-bit words. In plain English, it tells the receiving computer exactly where the header stops and the actual data starts. On the flip side, we have the reserves field. This one is entirely forward-looking. It's reserved for future use and, according to the protocol rules, should literally always just be set to 0.
And that brings us to Section 6, delivering the payload. After all that intricate structural breakdown, we finally hit the actual cargo. And what's really cool here is how the header adapts. The options and padding field is variable in length. It can hold different connection options and uses padding just to make sure the header perfectly aligns to a 32-bit boundary. And then, trailing right behind this highly secure, incredibly complex shipping label is the data itself, also variable in size. This is it, your actual email, the image, or the web page payload, all packed up securely for the final step of delivery. Let's just take a breath for a second and look at this quote straight from our source material. These fields work together to ensure reliable and ordered delivery of data between sender and receiver in a TCP connection. That is really the absolute core takeaway of this whole explainer. The exact structure might flex a bit depending on what options or flags are set, but this entire shebang exists for one single reason: total guaranteed reliability.
So I want to leave you with a final, provocative thought to chew on. Knowing all of this, the incredible synchronized dance of ports, massive sequence numbers, checksums, and those tiny 1-bit flags going into a single TCP segment, how many complete TCP headers do you think are flying across your device at this exact second? I mean, it's happening millions of times a second, totally invisibly, perfectly ordering the digital world right in front of your eyes. It is, frankly, a total marvel of engineering. Anyway, thanks so much for joining me on this deep dive. Keep learning, keep exploring, and I'll catch you in the next explainer.